Hello. So let's move on. In this lecture, we'll go over planar Couette flow, planar Poiseuille flow, and also molecular momentum flux. Okay. So let's first discuss planar Couette flow quickly. So it is in this flow we are considering two parallel plates. Okay, two solid parallel plates. Bottom one will be stationary. Top plate moving at a constant velocity of Vp. Now, in between there's a liquid, and obviously the flow establishes itself due to the viscous stress or the drag which is caused by the moving upper boundary, which is the upper plate. Now, this planar Couette flow you can find in a viscometer shaft bearing with a narrow gap. Okay, and for deriving the equation for this governing equation for this planar Couette flow, the assumptions made are that we are considering a steady incompressible fluid flow only in one direction, that is x direction. Okay, and it's fully developed flow. Now fully developed flow means dvx by dx will be equal to 0, meaning vx won't change with the x, okay, as it flows, as the fluid flows. And also pressure is constant along x direction, and we have gravity which is acting along the negative y direction. And now we can easily apply the continuity and the Navier-Stokes equations. Finally, the expression that we'll obtain are the x direction Navier-Stokes equation simplifies to d square vx by dy square equal to 0. This is for y direction, this is for z direction. So dp by dy is minus rho g and dp by dz is equal to 0. So these are the three equations related to the planar Couette flow. Okay, so this is the derivation. So in this figure, you can understand that h is the distance between the plates, Vp is the velocity of the upper moving plate, and fluid has density rho and viscosity mu. Bottom plate is fixed, and this is the derivation. In this point, in a single point, all the assumptions have been summarized over here, and the component of a Navier-Stokes equation. From this, we are eliminating all those terms which go to 0 and simplifying it using our assumptions. And and then you can go, this is the slide just for visualization of the picture actually, and these assumptions in one line. Moving on, finally these two are the equations that we'll get, okay, that you can keep in mind. Moving on, planar Poiseuille flow. Now again, there's a flow between two parallel plates, but here we'll have both of the plates to be fixed, and here the fluid motion is caused by application of pressure gradient along the x direction. It is analogous to circular pipe, fluid flowing in a circular pipe, and in this case laminar flow is also observed. Okay, now same assumptions will be same as planar Couette flow, however except here that we have a constant pressure gradient along x direction. In planar Couette flow, dp by dx was 0, here dp by dx will be some constant value. Again, using the assumptions, we'll apply the continuity and Navier-Stokes equations, and finally the Navier-Stokes equation for x, y, and z directions are shown over here. So mu into d square vx by dy square equal to 2p by 2x. So this right hand side is actually a constant, and simply this equation you can understand is that understand it as a balance of pressure force and viscous forces, and y and z directions same as Couette flow. Boundary conditions, this is second order ordinary differential equation, this one as you can see, and so we have two conditions which are given over here, obviously. Okay, so let's look at the diagram over here. So this is this middle line is where we are considering the x-axis to be. So upper plate is at h from above, and h below is the bottom plate. So that's why vx will be 0 at y equal to plus h, y is equal to minus h, considering the no slip condition. So again, this is the same picture for visualizing, and the same assumptions as you can see, and the derivation is also shown for the x and y component over here. Moving on, finally let's finish off this lecture quickly by discussing the viscous stress versus molecular momentum flux notions. So these are two viewpoints actually. This fluid mechanics viewpoint you can say, and this is the momentum transport viewpoint you can say. So molecular momentum flux, this is viscous stress. Obviously this is the flow of momentum flux. This this is a force per unit area which is acting all right. So in this case you can see force along positive x-axis on a positive y plane, and we are considering the usual planar Couette flow. If you can see the it is viscous stress exerted by fluid in a region of greater y on fluid in region of lesser y. So fluid which is has a higher y coordinate is moving faster than the fluid which is below it. So viscous stress is exerted by it on the below layer, and here viscous stress is proportional to the velocity gradient, and tau ix fluid this is we have seen in Newton's law of viscosity. So tau ix is equal to mu into dou Vx by dou y. This is something we know, but here Fm stands for fluid mechanics. So this is the viscous stress viewpoint. Moving on to the molecular momentum flux viewpoint. So actually, the fluid near, we are actually in this case we are considering an inverted planar fluid flow, as you can see, and this is the velocity. This is what the velocity profile will look like. Bottom plate moving with constant velocity Vp. Distance between them again h. What happens here is the fluid which is near the bottom surface which is moving, it acquires x momentum, and this fluid, it will in turn impart some of its x momentum to the adjacent layer, adjacent above layer, causing it to remain in motion in the x direction. So x momentum is transported through the fluid in the y direction. Okay, and that is why we have molecular momentum flux. So flux of molecular x momentum transport from positive y direction flows from region of lesser y to greater y, obviously, and it is proportional to negative of velocity gradient. You can clearly see over here. The molecular momentum is transported along the direction of negative velocity gradient, and the equation is tau yx tau x equal to minus mu into tau vx by tau y. So we have a negative sign over here, so that along the positive y direction we have positive momentum flux transported, and tau yx MOMT transform momentum transport. So this is what we get. Thank you, and with this we are complete. We will be moving on to energy balance in the next lecture. Bye.